My name is Tyler Hart, and my project is Supercritical CO2 turbine generator, and it was done through the Department of Mechanical Engineering. And I want to give a thank you to my advisor, Anthony Lin, as well as my teammates for their hard work. And some background on what turbine power generation is it's really just the conversion of energy through different states. You start with a thermal energy source, whether that's fossil fuels, nuclear energy, certain solar applications, and this gets transferred to what we call a working fluid, and that's typically like steam or the combustion gases themselves. And then that working fluid pushes the rotor of a turbine and creates rotational mechanical energy, and then this can be used to spin a generator and deliver that electricity as the final product. And my project focuses on this section, going from the heat to that rotational mechanical energy. And it's done through a cycle where that working fluid is going around through about four main components. And they take the heat in, and then that spins the turbine, and the energy goes out, and then you just need to cool that fluid down and pump it back up to pressure in order to restart that cycle. And essentially, this is a pretty fundamental thermodynamics lesson for any junior mechanical engineer at BU. And it used to be taught in a hands-on way with this old steam cycle in the basement of the Mechie building, but it's been broken for a couple years. So what my project aims to do is design a lab-scale prototype SCO2 turbine generator system to replace this teaching tool so that future students can use our system to gain that experience, learn these lessons about thermodynamics and turbomachinery. And the requirements that came with this is that we want this system to be able to be manufactured on campus, and we also want it to function in the same indoor setting, so therefore we need a small size to fit the pretty small footprint that the old system had. And supercritical CO2 is going to be the working fluid of this system. And to start with, supercritical essentially is a different phase of a substance. You know, we're used to solid, liquid, and gas. But if you add enough pressure and temperature and you get past what's called the critical point, the liquid and the gas are pretty indistinguishable, and it's just one supercritical fluid. And this high energy state comes with some special properties. And the reason we chose CO2 is that compared to water, the critical point of CO2 is at a much lower pressure and temperature, so it's much more achievable than the supercritical state of water. And then additionally, supercritical CO2 has a much higher working fluid density than water, and that basically just means for every unit of volume, the supercritical CO2 can hold more energy. So you can see on those two turbines down below, they're approximately the same energy throughput, but the CO2 system is much, much smaller. And this scale brings benefits. Each component, from the turbine to the pump, everything in between, is smaller. It can be less complex, and this just leads to cost savings. And this is why supercritical CO2 is being researched at kind of the forefront of power generation right now. And what lends itself to our project is that, one, it gives students a hands-on approach with this cutting-edge technology, but it also lends itself to the smaller form factor to fit in that demonstrator footprint in the Mechie space. And the first part of this project is deciding the state of that CO2 in between each of our four main components. So you see the cycle on the bottom left. Those are our four main components, and essentially in between each, our design is picking the pressure and the temperature at that point, and that sets the inlet and the outlet conditions for each of those components and is critical to starting the design phase for each of those. And some of the limiting factors we faced during this design phase was that corrosion can occur in the materials we were looking at higher temperatures. So we chose a lower max temperature, and this hurt our efficiency in the end. But obviously, you wouldn't make a grid scale system at only 14% efficiency. But that's not the main goal of our project. It's a demonstrator tool. So the safety and the feasibility took priority. And lastly, our thermocycle design ended up being from 7 to 15 megapascals, and these are very high pressures. So containing those pressures and being able to take it from state 1 to state 2, that high pressure increase is a big design challenge in this process. And one of the most important components is the turbine, and this is the part where the fluid enters at its highest energy state, and it spins the turbines, which are in red here, and that transfers the energy from the fluid to the rotation of that shaft, which could go to a generator. And to solve that high pressure issue, we used a double turbine, so you see the fluids entering at both sides, and so this can cancel out where you'd otherwise get an axial load on that turbine disc. We're able to solve that problem and deal with those high pressures by using the offsetting turbines. And another important point is that the blade geometry is limited by what we have access to for fabrication in EPIC on campus, because we only have 4-axis milling at EPIC, whereas real turbines have very complex blade geometries which need special machines or casting to accomplish it. So to validate our designs for the blade geometry, we are creating an aluminum prototype turbine instead of the final steel design in order to test those geometries and validate our design decisions. And another big piece of the project for myself is this supercritical transition viewer, which you can see here. And you can actually look at it closer later if you find me. And it's another classroom demonstration tool, and it's a visual of that supercritical phase transition to sort of explain to students, both in these thermodynamic classes, but also maybe in like chemistry classes, what that supercritical transition looks like. And you can see it going from liquid and gas, and then you put energy in, and it becomes one supercritical fluid. And it's a pretty simple operation. You would load some dry ice into the cavity of the aluminum block, bolt it all together, apply that little heat to get it above the critical point, just above room temperature, and you can watch the transition happen. And the process of making this device was a big learning process for myself. I didn't have much experience programming or using the mills on campus, so it was a really cool experience to take a solid chunk of aluminum and turn it over time into this finished piece. And as well, I got to use those thick acrylic windows that let you see into the chamber. That was also done on the mill, and that leads itself to a final product, all assembled. And you can see here on the video on the left, we load that dry ice in. It melts as it comes to pressure. And then as it warms up, it can sit around room temperature like it is now in a stable 2-phase state. So there's liquid on the bottom and gas on the top. But when you put it on a hot plate on the right, you add just a little bit of heat, and it becomes one continuous fluid. If this video plays, you can see just on the top the kind of characteristic turbidity of the fluid going around. But more importantly, you can notice that there's no no liquid and no gas phase anymore. It's just one continuous fluid. And this is the supercritical state, and this is the fluid that would be going through our final turbine. And to summarize, our project essentially set the framework of this supercritical CO2 turbine system through the cycle selection, the primary 4 component designs, as well as validation through the machining of the prototype turbine, and as well as delivering the additional teaching tool in the supercritical viewer. And obviously, the final goal is to deliver a full functioning system to the mechanical department so these future juniors can learn about thermodynamics. And so another senior design team would need to take up this mantle and do the circuitry and controls to ensure safe operation of the system, as well as the instrumentation for students to be able to collect enough data to run their experiments and really understand how the system is functioning. And then, of course, lastly is building out the entire system to allow the students to really get hands-on and, engage with the material. Thank you.
Any questions for Tyler?
So with the viewing tool, how often would you have to replace the dry ice, if at all?
I mean, currently it's held 50 grams of CO2 at pressure in there for almost 2 days now. So hypothetically, you can kind of just stay in this liquid gas phase and then heat it up as needed. But for long-term storage, you could vent it. And I bought 5 pounds of dry ice for $20 in Brookline. And it's only 50 grams to fill it up enough, so it's really not too expensive.
Great job. I had a question. So you said that they previously used like steam turbines for the demonstration. What's the advantage of using, for the educational purposes, a supercritical CO2 generator versus steam? Why would you not just rebuild or buy a new steam turbine?
It essentially just adds another layer of where they get to sort of explore the extra dimension of why would the industry be researching this new fluid, and sort of compare it to, all the problems you work through in class are kind of using steam, but you could compare this new experience to the classical things they learn in their lectures, and it was also kind of just a cool element to add to our project.
All right, great job, Tyler.